Okay, welcome to part 5 of the standard ASHEE tutorial. And so we have just finished step 7, setting up the simulation parameters in this control dict file that we were looking at. Now we're up to running case set to get ASHEE to set the case for us, for our specific case. Okay, so at the moment we're in, if I print the working directory, we're in this plume test folder we created, set scenarios, folder 0 system. We want to get back to this set scenarios folder here. So how I'm going to do that is I'm going to write cd ... And you see I go from folder 0 system back down to folder 0. So if I do that again, then I end up in the set scenarios folder that I want to be in. If I look at what's in that folder, you can see I have my 2 folders, my 2 files. What we need to do now is just make sure that everything in this dat folder is empty, so make sure there's nothing hiding in there. So I'm going to rm for remove dat / star. So the star will remove every single thing in that folder. Okay, well it turns out there's nothing in there at the moment, so that's good. But it's always worth doing that just in case. Now what we want to do is run case set. Okay, so /case set.sh for shell, and we just enter that and run it. Okay, and you can see that now we've created something here. This is actually a new folder. So if I type ls, I can see that now I had the dat in the folder 0 before, but now I've got this extra folder. Okay. And so it's got this funny name. So Q 1.0 e to the 8, that's actually our mass flow rate. So 1 × 10 to the 8 kilograms per second. T 1200, well, that's the temperature of the plume at the vent. Y 5.0, well, that's saying that our mass fraction of water at the vent is 5%. MA 0.75, so now we've got a Mach number of 0.75, and R4. So this is the number of cells at the vent. So there's 4 cells across that vent. Okay, so that's why it's got a funny name, but it is quite an informative name. Okay, great. What do we do now? Well, we've done part 8 now, which is quite easy. We want to navigate into our newly created folder and execute this thing called case run. So we'll cd into this new folder we created, and then quite simply /case run.shell. Okay, so if I press enter, hopefully we get no errors. It takes a little bit of time to run through, and so assuming this exits without any errors, basically set up our simulation. Okay, I'm just going to press ls here, and I just want to point out one thing. We have a lot of things in here that we can look at, but the main thing I want to point out now is processor 0, processor 1, processor 2, and processor 3. So we've got 4 processors there. So if you remember, earlier on when we were setting the nproc inside the case setting file, we set that equal to 4. So the number of processes we want to run the simulation on is equal to 4. So if you've done that and you don't have 4 folders here, then you've done something wrong. So it's just a nice, I guess, sanity check, right? Okay, great. So the other thing we can do from here is if we wanted to, we could move into the, where is it? The system folder here. Okay, so I'm just going to go into the system folder just to check what's in there. So if I list what's in that folder, I have a lot of things that we've seen before. Control dictionary, we modified before. There are some things like cutting planes here and probes. So we might just have a quick look at one of those. Cutting plane.h. Okay, so this cutting plane basically it takes a slice through results, and so that we can just view one slice of the results rather than the whole three-dimensional eruption. So you can set down here where you want that cutting plane to be, the X, Y, and the Z coordinate, and then the normal vector of that plane. So this is pointing X, Y, and Z at 0, 0, 0.57. And the normal vector of that is just pointing in the X direction. So you get something that's basically a horizontal, a vertical slice. I'm actually going to skip this part because we can actually do this once we've run the simulation. We can do this manually anyway. And I think it's slightly better to do it manually because then you can see your results and then decide where you want to, for example, look at one of these planes or look at where we want to put a probe. So for now, I don't think we need to do that. So I'm going to skip looking at the probes.h as well. So what I'm going to do though is list again what's in here. One thing we might want to look at is the finite volume schemes, this one here. So I'm going to gedit finite volume schemes. Schemes. I need a capital there. So this is just really for your information. There are various numerical methods that we can choose in ASHEE to solve certain parts of our governing equations. This just tells you what finite volume schemes you're using, what numerical methods you're using. Okay, we're not going to change any of this at all. It's unlikely that we'll ever need to change any of this. But just so you know, if you're ever looking for this information, perhaps if you're writing a paper and you need to include that information in the paper, you can find that in this finite volume schemes. The only part that we may look at is in finite volume solution. So I'm going to close this and look at gedit finite volume solution. Okay. So again, this has a lot of information about certain solvers that we're using. And again, you're probably not going to have to change these at all during the time. It has some tolerances to these solvers, but again, you're probably not going to have to change these at all. One thing to notice down here is this thing called Pimple. This is a sort of a method of solving a compressible set of equations. You have options here to change the number of correction terms. So you can increase these numbers if you like, which in theory should give you a more accurate result, but will actually make your result a lot slower to compute. Okay, we have some options here. Do we want to track the deposit as it grows over time? I would always leave this as true. Are we doing an isothermal simulation? So is temperature changing? It's always going to changing. Zero order, you always want this to be false because, well, if this is true, then we couple the acceleration and settling. So we want this to be false so that settling, particle settling and acceleration is decoupled from the main flow. If we set this to true, then we only have decoupling of settling, but acceleration is not decoupled from the gas flow. If we set this equal to true and we set the particle size as equal to 0 in previous file, that'd be like a dusty gas approximation. Transonic, if you want to be able to track shocks, this also needs to be true, so that slightly changes the numerical method. But in really, I think we can leave that. For Mach number less than 1, you could set this to false, but it's safer just to leave it as true as it is. Okay, so again, I don't think we need to change anything in that, but this is just more of a for your information. There are bits we can play with here if we need to in the future. So we're actually, believe it or not, ready to run our first simulation. So what I'm going to do here is I'm going to go up one level so that I'm currently in the plume test set scenarios and this folder we created, which has our specific simulation parameters in it. Okay, and the command to run is like so. MPI run, so we got a multi-parallel implementation run. Negative NP, so this tells us the number of processes. So remember, we chose that to be 4. So this has to be equal to the same number that you chose for the number of processes, which in our case was 4. We're going to run ASHEE. We're going to go negative parallel. So we're going to run this in parallel. And I'm going to write greater than log 0 ampersand. Okay, log 0 thing, the greater than log 0 thing. So we're writing a log file so we can keep track of the simulation. The ampersand is just to allow us to keep typing in the same terminal. So we just type that here and press enter. And hopefully, if nothing's wrong, it'll run. Okay. So I think that's running. How we can check that is we can, there's a couple of ways we can check. If I type head minus 300 log 0, then this gives me the first 300 lines in the log file. So this is basically the starting commands that, I might make this larger, the starting commands that ASHEE is starting to run. It's reading all these fields and now it's starting to run. Probably the more useful one is tail, let's say minus 100 log 0. And so this gives us the last 100 things that ASHEE has done. So I might just clear this for a minute and write tail maybe minus 500. So this is the last 500 lines that ASHEE has done. So it's been running apparently for 40 seconds. Let's see, it gives us information on the courant number and the max courant number. This is interesting to tell us about. It must be less than that, 0.2, as we set in one of the earlier files. And if we scroll up, eventually, hopefully, we should find something like this, time. So remember, we were trying to run this for 3,600 seconds, or in other words, 1 hour. At the moment, ASHEE has got through 0.3 of those, almost 0.3 of those. So if I continue, if I write clear again, and I say tail negative 500 log 0, every time I type that, it'll give me the most up-to-date information. So I'll look up here now, ASHEE's actually run 7 seconds of the simulation already. So now basically we can just occasionally check on this by, now we've run 11 seconds. Basically now we can just let this run, and once we're finished running, assuming we don't have any errors, we'll come back and I'll show you our results.